Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome everyone. I'm delighted to see so many people attending the Northwest Probability Seminar. It's our annual Northwest event, and I'm happy to see that it's going so well. Well, I have the pleasure of introducing the first speaker. Actually, the first speaker did a great job of introducing himself. Ander Holroyd, who is representing Microsoft at this mini conference, will talk about finitely dependent colorings. Although, sorry, just one. Coloring. Please.
Okay, thank you. Well, wonderful to be here and see so many people. So, what I'm going to talk about is some new and rather strange and mysterious object that we found, a stochastic process. I think it's fair to say that we don't fully understand how it works. I mean, we can prove a lot of things about it, but we don't entirely know what's going on. So I'd certainly be pleased to have any help that anyone can offer on that. So it's joint work with Tom Liggett, and it's dedicated to Oded Schramm, and I'll explain why. So the basic motivating question, I guess, is do local constraints demand global organization? So, I mean, there are lots of questions in real life that sort of fit into that category, I guess. So you know, do you need national banks to organize financial transactions? Do you need national borders? Do you need central planning of road networks, or could you just let roads sort of evolve and organize themselves like they did for many centuries? So, of course, I don't have any answers to those questions, but I want to talk about a very, very simple, clean mathematical question, which is a version of that general question. And before I state it formally, I'm going to just tell a little story. I hesitate to say application because it's not really that realistic. It's just a story. Imagine you have a network of machines, computers, and simplest type of network of all is just a line, the integer line. And suppose you want to assign some schedules to them, say schedules for updates when the machines update their software or something like that. And for simplicity, let's say the schedule is simply a day of the week, so you want to assign a day of the week to each computer when it's going to do something. So maybe we just update them all on Mondays, but maybe that's a bad idea. Maybe we have some local constraints, and so perhaps we have the local constraint that adjacent machines, you don't want to update them at the same time because maybe that creates a conflict. So maybe you want to update adjacent machines on different days. So you could, for instance, alternate Monday, Tuesday, Monday, Tuesday. So now suppose I also have a security constraint, and my security constraint is that I would prefer adversaries not to learn too much about my schedules. So the best way to make something secret is to choose it at random. So I want to choose the schedules at random in some way, and I want it to be the case that if somebody finds out some of them, then they don't find out too much about the others. So, for instance, maybe they find out the schedules of these two here, and I would like that doesn't give you too much information about the others. And now it's bound to give you some information, because if you know that this one is Monday, then because of the local constraint, you know that this one cannot be Monday next to it, but maybe you can hope that it doesn't give you too much information about other machines further away, some larger distance away. Okay, so let's just, that's the story. Now let me turn it into a mathematical question. So here's a question, which arose from discussions between myself and Itai Benjamini and Benji Weiss in 2008. So fixed integers k and q. Does there exist a stationary k-dependent q coloring of the integers? And of course, I will tell you what these words mean. So by a q coloring, I mean a random sequence indexed by the integers, assigning a color, which is just an integer from 1 to q, to each integer. The whole sequence is random, and I want it to be a proper coloring, which means that adjacent integers must have different colors. Okay, that's the local constraint. And stationary, of course, we all know what it means. If you shift by 1 to the right, say, the sequence, you get a sequence with the same distribution. And the most interesting condition is k-dependence. And this says, if you take two sets of integers which are more than distance k apart, then the random vector that you get by restricting to this set is independent of the random vector that you get by restricting to this set. So you ignore k guys in between, and you look at some set of integers here and some set of integers here, then the colors I see over here should be independent of the colors I see over there. Okay, so that's definition clear? And of course, you know, the integer line z is only one graph. There are many others, and I'll have something to say about other graphs later. And proper coloring is just one local constraint, and I'll have something to say about other local constraints later as well. But it turns out that this simplest case is also the key case in a certain sense. So again, the question is, does there exist a thing like this? It's coloring, and it's k-dependent, and it's stationary. So let's just try some simple and in some cases foolish attempts, some things that won't work. So suppose you just try to have identically distributed colors for each integer. You just have some distribution over the colors, and you choose them IID. So of course it's stationary, and it's zero dependent because anything is independent of anything else. But of course it's not a coloring because there must be some color, say color 1, that has positive probability p, and that means you have probability p squared of seeing two 1s next to each other. Okay, so obviously it doesn't work. I mean, let's try something that obviously is a coloring. If you have two colors, you can certainly just have them alternating 1, 2, 1, 2. Well, that's a deterministic sequence. That's not stationary. But if I want to make it stationary, then there are exactly two deterministic two colorings, where I alternate red, blue, or I alternate blue, red. And if I choose this whole sequence with probability half and this whole sequence with probability half, then of course I have a stationary process. But it's not k-dependent. It's not anywhere close, because if I know x0, I know whether it's red or blue, then I know xn for any n. So no way x0 and xn are independent. One determines the other. So of course that doesn't work. So another thing that you might try, which also won't work, is just make the coloring as random as possible. So just essentially choose uniformly. So choose x0 to be a uniformly random color, and then choose x1 to be uniformly random from the colors that are not the same as x0, and so on in sequence, and do the same going the other way as well. So of course this is just a stationary Markov chain with that transition matrix. So it's stationary and it's a proper coloring, but of course, it's not k-dependent for any k, because you can just compute, given that I see a 1 at 0, you can compute the probability I see a 1 at n, and it's decaying towards 1 over q exponentially fast, but it never reaches 1 over q. So these two events are never independent. So that's not a k-dependent process. So that won't do. Now, okay, so thinking about Markov chains still, there are k-dependent Markov chains. So here's a 1-dependent Markov chain, just to understand the definitions a bit better. So the state of the Markov chain is that you have 4 states, and this corresponds to having 2 coins in your hands. And the move of the Markov chain, the step of the Markov chain, is you exchange the 2 coins and you retoss one of them, say the coin that ends up in your left hand. So maybe you start with head, and then the first step, you just move this coin down there, and you retoss that one. So maybe it becomes tails. Now you have tail head. So that's the step of the Markov chain, and you keep going. So it has some transition matrix. So this is a one-dependent process, because as soon as you've taken 2 steps, you've tossed both the coins, so you've completely forgotten where you came from. So x0 is independent of x2, but more than that, all the past up to x0 is independent of all the future from x2 onward. So it's a one-dependent process. But of course, it's not a coloring, because you can perfectly easily make the transition from head to head. Okay, so of course that doesn't work. So it turns out no Markov chain will work. So no Markov chain, no stationary Markov chain can be a k-dependent coloring. So why is that? Well, if it's k-dependent, then what's the probability that you see a particular color, say color B, at time k plus 1, given that you saw color A at time 0? Well, as k plus 1 is bigger than k, these two events should be independent, so that should be just the same as the stationary probability of seeing color B. So in particular, it's the same as the conditional probability of seeing color B after k plus 2 steps as well. Okay, so that means the matrix, the transition matrix, satisfies this. P to the k plus 1 equals p to the k plus 2, and that means the matrix satisfies this equation. So the eigenvalues of the transition matrix are precisely 0 and 1, but perhaps with multiplicities. On the other hand, if it's a Q coloring, then that means the transition from color A to color A happens with probability 0. So that means the matrix has zeros all along the diagonal, so that means the trace is 0. But the trace is the sum of the eigenvalues. And the eigenvalues are 0 and 1. Okay, so that's impossible. So we can't do anything with Markov chains. And furthermore, you can say more. So Oded-Schramm proved that there's no hidden Markov k-dependent Q coloring. What does that mean? It means you have a Markov chain on a finite state space. The finite state space is important. And then X is just some deterministic function of the Markov chain. So it's just you collapse some sets of states into one if you want, and that gives you the process. So even that won't work. There's no such thing. And this covers many things that you might think of, like k-step Markov chains, which is where where you go next depends on the last k steps and so on. And Gibbs measures with local interaction. Those are just Markov chains on the integer line. This is proved by similar ideas to the very simple proof I just showed you, but in a more complicated setting. Oded-Schramm, as is well known to almost everyone here, central figure of his generation in probability theory, passed away in a tragic hiking accident in 2008. This problem that I'm talking about was actually, he became very, very interested in, and it was one of his favorite problems in his last few months with us. So this is one of the reasons that I've been so keen to try to make some progress on it, to come up with something that Oded would have been happy to hear, and I think we've succeeded, as I will try to show you. There's another potential source of examples, and maybe this would be one of the first things you would think of, in fact, when I mention k-dependent processes. So that's about a block factor. So so suppose UI is an IID process of IID random variables on any space, and f is any function which takes r arguments, and we just let xi be f of a block of consecutive u's like this. So say r is 3, you have these independent u's, and you take some function of these 3, that's x minus 1, you take the same function of those 3, etc. Right? So this is automatically going to be so it's called an R block factor of an IID process. The process X is. So it's automatically going to be K dependent for I guess K equals R minus 1, because if these blocks don't overlap with each other, then certainly the X's over here are independent of the X's over there. Now, for instance, this coin example I showed you is actually a two-block factor of a sequence of coin tosses, because you can think of it as another way. You can just think of a sequence of fair coin tosses, and then you just look at the pairs. You look at this is head-head, this is head-tail. Turns out that's the same process. But then there are other examples which are not Markov chains, which are really a new type. So a simple example is just take uniform random variables, uniform on the interval 0, 1. Here they are, and see which way the inequalities go between them. And write down a 0 if the inequality goes this way, and a 1 if the inequality goes the other way. Okay, so that's kind of an interesting stationary process, and it's really a different type. It's not a Markov chain or a hidden Markov chain. But of course, it's not a coloring, because you can perfectly easily have two 1s next to each other. So an R block factor is an R minus 1 dependent process, because, as I said, if the blocks are far enough apart, then the random variables are independent. And you might wonder whether these are the only K-dependent processes, whether there's an implication in the other direction. And this question, so this has nothing to do with colorings right now, it's just the difference between block factors and K-dependent processes. So this question has kind of an interesting history. So the answer is no. So there are counterexamples. And this was stated without proof in a Russian book by Ibragimov and Linik in 1965. And they proved for Gaussian processes that it is equivalent. There are no counterexamples. And this question received quite a lot of attention. It was explicitly stated as an open question by a number of people. And finally, the first published solution, at least, was by these people, Aronson, Gilat, Keen, and De Valk in 1989. So they came up with a counterexample, but it was kind of a little bit of a strange, indirect proof, and they asked for a natural example. And then there's been a whole sequence of papers, people trying to come up with better, more natural counterexamples. There's an explicit Markov chain that people came up with, and then one breakthrough is Burton, Goulet, and Meester found even a one-dependent process that's not an R block factor for any R, and that's a hidden Markov chain, it turns out. And there's another 20 papers on this, with people trying to just really understand what the difference is here and come up with more natural examples. But the general belief, I think, was summed up by Borodin, Diaconis, and Fulton. This is particularly for one-dependent processes. They said it appears that most natural one-dependent processes are two-block factors. So all these counterexamples that people came up with were kind of a bit contrived, and it seemed like the only examples anyone could come up with were ones that were specifically constructed for the purpose of counterexamples. I think that's a fair summary. Now, this is interesting because turns out block factors will not help with our question. So no block factor coloring exists for any R and any Q. And this is one of these results where it's a little bit hard to know whom to attribute it to. There's essentially an equivalent result proved by Moni Noor in 91, although stated in a very different language from how I'm stating it now. you can argue it's really a variant of Ramsey's theorem. But anyway, it's a fact. And in fact, one can say more. So here's a very clean statement and an interesting, perhaps little known statement. If you have any IID random variables and you have a function of R arguments, which just takes finitely many discrete values, 1 up to q, and you look at the event that f of u1 up to ur is equal to f of u2 up to ur plus 1, then that is strictly positive for any function. And moreover, there's an explicit lower bound that you can write here, a very, very small lower bound, but it's strictly positive with the tower function. And this is essentially tight to this tower function form. There are examples that are more or less like that. And let me show you why this is true. I won't prove this tower function, but I'll give you I won't even show you the proof, but I'll just tell you the idea of it. And from this slide, if you went away and spent 5 minutes, you could reconstruct the proof. So I'll just prove that it's positive. So you have a function and you have IID random variables. This is strictly positive. It'll be by induction on R, the length of the block. So of course, R equals 1 is easy because the blocks are just length 1. So f of u1 and f of u2 are independent, discrete random variables. So that's the argument I showed you right at the beginning. So the inductive step is the following. At least here's the key step, and once you've done this, it's not hard to finish the proof. So I'll define a set-valued function of r minus 1 arguments. And what it is you look at f, and you fix the first r minus 1 arguments, and you allow the last one to be random. And you look at which values, which colors A, this can take with positive probability. Okay, you look at the set of all those colors when UR is random. And that is a set-valued function of r minus 1 variables. So in particular, it takes at most 2 to the q values because it's a set of the numbers 1 up to q. And you apply the inductive hypothesis to that. You think of this as a block function of a block of r minus 1 variables. Apply the inductive hypothesis to that, and everything falls out. And you can see why you would get this tower function bound, because in the inductive step, I've gone from q colors to 2 to the q. And you have to do this once for each step in the induction. Okay, so back to the question. So is it possible that there could be a stationary k-dependent q coloring? And it's really looking like the answer ought to be no at this point, because we've tried Markov chains, we've tried hidden Markov chains, they cannot work. And we've tried block factors, they cannot work. So that only leaves these unnatural counterexamples that people really struggle to come up with of k-dependent processes that aren't block factors. Seems very unlikely. So Oded actually proved that it's not possible in the sort of first non-trivial case of K and Q, which is 1 dependent 3 colorings. So we saw right at the beginning that 2 colors isn't enough, but 3 colors and 1 dependent also doesn't work. And well, Oded conjectured, and I think all of us who were thinking about the problem at the time agreed as well with this conjecture, that it's not possible for any K and Q. Oded even reduced it to a problem of functional analysis. If this weird thing exists, then there's a Hilbert space with some strange properties. Indeed, there's no finite dimensional space. Nazarov and Denisov came up with a complex Hilbert space example, but it has to be a real Hilbert space, so that doesn't help. So this was where the problem rested for quite some years, until I started talking to my co-author, Tom Liggett at UCLA. And I hope he doesn't mind me sharing this story. I told him about the problem. He was kind of interested. After a week or so, he said, I think I can prove Oded's theorem that there's no one-dependent 3 coloring. He proved it himself, so I said, great, that sounds good. And he said, so now I'm going to look at 4 coloring. And then a week or two later, he said, I think I can also prove that there's no one-dependent 4 coloring. And now I'm going to move on to 5 colors. And I said, that sounded good. And then a few weeks later, he said, I think there was a mistake in that last proof. And now I think there is a one-dependent 4 coloring. And I was very skeptical about this. So we managed to come up with this incredibly complicated formula, which I won't go into, but if you're interested in dict words and linear extensions of posets, then I can tell you about it afterwards. It's kind of interesting. So what this purports to be is A is the cylinder probabilities for a one-dependent 4 coloring. Okay, the finite dimensional distributions. Some weird formula, and we were able to prove that this satisfies what it needs to satisfy for one dependence and stationarity and being a 4 coloring, but what we couldn't prove was that it was non-negative. It has to be non-negative if it's a probability, and of course that's always the hardest thing typically because it's an inequality. Inequalities are much harder than equalities often, and you see it's an alternating sum, so it's not at all obvious. And we struggled for 3 years over this. We had all sorts of special cases that we could prove. We checked billions of cases by computer and so on, but we really couldn't do it until we found another way, which I'm going to tell you about. So there is a one-dependent 4 coloring. And so a number of consequences, in particular, this old question about the difference between block factors and colorings. Now there's a beautifully clean answer to it. Coloring can be done by one-dependent processes, but not by any block factor. So that's very nice and interesting. And it answers some other questions about hidden Markov processes. And this weird Hilbert space exists. I don't know whether anyone cares about that now. This previous complicated formula I showed you is also correct, and that leads to a number of combinatorial identities, which I don't know how to prove any other way. Interesting combinatorial identities. So that's the coloring. So here are some weird properties that it has. This is a very, very strange process. We don't understand what's going on fully. It's symmetric under permutations of the colors. Maybe not such a big deal. So if you exchange red and green and permute the colors any way you want, you get a process with the same law. Here's something interesting. If you just look at the ones, so if you just look at the red, say, that's some process. Look at the indicator of where you have a red dot, then that's the following process. You take fair coin tossers and you look at the places where you see head-tail in sequence. Perfectly nice process. Obviously one dependent because it's a 2-block factor. That's what the reds are. If you look at 1 or 2, so you look at the places where you see red or purple, the indicator of that event, that gives you a process of 0s and 1s. And that's this process that I told you earlier, where you take IID uniforms and you look at which way the inequalities go. Very strange. And because of the symmetry, this holds for any pair. So in particular, try to think of any process on 4 colors so that if you look at any pair of them, 1s and 2s or 1s and 3s, etc., you get this process. So I know of no other example, and possibly this characterizes the process. We don't have a simple proof of this, really. We conjecture that the one-dependent 4 coloring is unique, actually. And this property is true for any stationary one-dependent 4 coloring, to the first one. Okay, nevertheless, despite all these strange mysteries, I'll tell you how to construct the process. It's very simple. I'll tell you 2 ways to do it. First one, start with just IID uniform colors, uniform on 1 to 4. Okay, we know this is a silly thing to do, of course. But now I'm going to condition on something, and Right, so I'm not just going to condition on the event that this is a proper coloring. Yeah, so I should have said, what I'm going to do here is I'm just going to tell you the finite dimensional distribution. So I'll tell you the joint distribution of x1 up to xn, okay, and it will turn out that this is a consistent family of distributions, okay. So first of all, I choose IID uniform colors. Now I'm going to condition on a certain event. And the event is not just the event that I have a proper coloring. That would be too easy. That would give me the Markov chain that I started off at the beginning. Instead, I choose an independent, uniformly random permutation of 1 up to n as well. And I think of these as arrival times. And I'm going to condition on the event that at each time, the subsequence that has arrived so far is a proper coloring. And I'll show you what I mean with the example. So here are my colors. And then they arrive at these random times. So at time 1, all I see is blue. At time 2, I see blue, red, because that red guy arrived. At time 3, I see red, blue, red, which is good. At time 4, I see red, blue, red, red. And that's not good, because that's not a proper coloring, because I have 2 reds next to each other. Even though there were some other things that were going to arrive in between, it doesn't matter. So I condition on the event that at every time, the subsequence that I see so far is a proper coloring. So you see in this case, because I have 2 reds next to each other at the end, no matter what permutation I chose, it wouldn't work. But if it was a proper coloring, then it might or it might not, depending on the permutation. So that's it. I condition on that event. That gives the correct law of x1 up to xn. It's obviously a coloring, but is it obvious to you that this is a one-dependent process? It certainly isn't to me. Here's a second construction. Here's an equivalent way to do it, and it's not too hard to show that it's equivalent to what I just told you. Start with a random color, uniformly random. Now I'm going to insert extra colors. So maybe I insert a red to the left, and maybe I insert a blue in between, in the middle. Maybe I insert a red there. So what's the rule? The rule is at any time you have these possible slots where you can insert at the end points or the internal slots. And how many possible colors are there that you can insert? Well, at the end there are always 3 possibilities if you want to make a proper coloring. And in the middle there are always 2 because these 2 colors are different, so there are 2 things that could go there. And you choose uniformly from these possibilities down there. So you choose the position proportional to the numbers 3, 2, 2, 2, 2, 3, and then once you've chosen the position, you chose a random color. Again, that's it. You do that for n steps, you get a random vector of length n, and turns out these are consistent distributions, and they're the ones I want. Yeah, well, I don't have time to talk about the proof, but it's the proof that this works is quite simple. It's only a page or 2. You can express this probability as the number of what we call buildings, which are permutations that work for that particular coloring, divided by the sum of all of them, and the denominator is something innocuous. And there's this lemma: the number of buildings of x is equal to the sum of the number of buildings that you get by deleting the elements one at a time. That's obvious if you think about it, because you just see which was the last element that was added. And you just have to prove this, that the number of buildings, if you sum over this color in the middle and you have a word here and a word here, these are supposed to be independent. So you're basically trying to show it's equal to that product. And you just expand using this lemma, you split into some cases, you use induction, it just works. So what about other k and q? So here's a very easy way to get a 3-dependent 3 coloring. Start from the 1-dependent 4 coloring, eliminate color 4 wherever I see it, and replace it with something else. Replace it with just the smallest number that's not represented among the 2 neighbors. So this is a block factor of the original coloring. It's a 3-block factor because what I put here only depends on myself and the 2 neighbors. So if you think about it, that means it's 3-dependent, and it's a 3 coloring. So that only, we know that 1-dependent 3 coloring can't be done. That only actually leaves 2-dependent 3 coloring. And we were getting all ready to say this is an interesting open problem, and then we realized that can be done as well. And the astonishing thing is, and this just blew me away, the same process works. So these two constructions that I gave you, they're equivalent. You can do the constructions with any number of colors. You always get a consistent family of distributions, it turns out, so you get a coloring on the integer line. And with 4 colors, it's 1 dependent. With 3 colors, it's 2 dependent. With any other number of colors, it's not k dependent for any k. Very, very strange. So there's something absolutely magical about 3 and 4, which we still don't fully understand. Is that there are very few other colorings, k-dependent colorings known. You can do embellishments of these, like the thing I just showed you with the 3 colors. And there's one more family of examples, which I maybe won't have time to talk about. Interesting properties of the 3 coloring as well, so that this 3 coloring I just told you is just the 4 coloring conditioned to have no 4s, at least on a finite interval. So why should that work? I have no idea, but it does. Why should it work that if you take a 1-dependent 4 coloring and you condition it to have no 4s, you get a 2-dependent process? No idea, except we have the proof. Also, if you look at the locations of a single color, 1, in the 3 coloring, those have a beautiful form as well. You take these IADUs and you look at the peaks. You look at the place where the U is a local maximum. Turns out that's what process it is. So remember this strange thing about the 4 coloring, that 1s and 2s have a nice interpretation in terms of the U's. So you would really think there was some connection between these 3 facts here. The 3 coloring is what you get by conditioning the 4 coloring, and this has this nice property with U's, and this has another nice property with U's. I have proofs of each of the 3 things, but they're completely different, and we don't understand what the connection is. I'll skip that. I will skip this. Well, I'll just say a word. One can define more general local systems of constraints. Coloring is just one constraint, but you can say, on windows of length 3, I'm only allowed to see this finite list of things. That gives you what's called a shift of finite type. You can extend some of these things to shifts of finite type. So if you have any system of constraints like that, throw aside some degenerate cases that don't matter, then you basically have the same thing. You can satisfy it with a k-dependent process, and you can not satisfy it with a block factor. So there's an even more remarkable answer to this old question. So any shift of finite type, if you want your process to do anything at all, non-trivial, then you could do it with a k-dependent process, and you cannot do it with a block factor. We can say some things about ZD as well, but lots of things are open, and I don't have time for that. And there are lots of open questions. Uniqueness. How many colors do you need on ZD for a 1-dependent coloring? We know it's between 9 and 16. Can you express it as can you express one of these colorings as a function of a countable state Markov chain? We know you can't do it as a function of a finite state Markov chain, and on the other hand, any process can be expressed as a function of an uncountable state Markov chain. Shifts of finite type in d dimensions is a big, very complicated area. We don't have much to say about that. But yeah, I guess the bigger question is just what's going on here. Is there another way of thinking of these processes that make the properties more obvious? So I'll stop there.
Any questions or comments?
Did I understand it correctly that your construction doesn't work for 5 colors because it's not k-dependent?
Right, the construction works, so it gives you a stationary 5 coloring, but it's not k-dependent for any k.
So do you have a construction then for a larger number of colors?
Right, great question. So yes, so I mean, first of all, there are some trivialities, right? So a 4 coloring is a 5 coloring, So done.
Okay.
If you want positive probability of each color, then you can just split a color. You just, whenever you see color 4, you toss a coin and make it color 5 some of the time. Okay, but you might ask, is there a symmetric 5 coloring, for example, symmetric under permutations of the colors? The answer to that is yes. This is one of the things I didn't really have time to say, but we managed to come up with a family of symmetric one-dependent Q colorings for all Q greater than or equal to 4, and this we understand even less than the other thing, if that's possible, but it is a proof. So there's a much more complicated recursive formula for the probability in terms of the things that you get by deleting one symbol at a time. With these are Chebyshev polynomials, which can also be expressed in terms of hyperbolic functions with this word parameter. So yes, but we don't really understand why it works.
So it's symmetric under all Q factorial?
Yeah, symmetric under all permutations of the color. Yeah.
Any other questions or comments?
So this formula doesn't make sense for Q equals 3?
Right, for Q equals 3, there's some 0 over 0 or something like that.
T is not real.
No, T is real. Yeah, good question. But yeah, for Q equals 3, it's exactly where it breaks down somehow.
Well, if there are no more questions or comments, let's end it in.